We're going to define now projections of vectors in inner product spaces. We talked about lengths of vectors, distance between two vectors, and angles between two vectors, angle between two vectors. Now we can define projections. So here is a diagram of this idea. Here we have two vectors u and v, and the projection of u onto v is going to be this red vector here. So projection of u onto v is another vector, and that's the diagram of the definition. Now here it's one case when the angle between the two vectors, theta here, is less than 90 degrees, but we could have another situation which is like this, where the angle is greater than 90 degrees. So in that case, the projection will actually be this one here. So it's the shadow of u onto v on the direction of v. So notice that projection of u onto v goes in the other direction of opposite to v. Okay. So let's look at both cases, and in both cases we're going to get a formula, and the formula will be the same. So let's take a look at this first one. How do we get the formula for projection? So we need two pieces of information. We have two pieces of information here. Number one is that projection of u onto v is on the same direction as v. So it's a constant, or it's a multiple of v. Okay, so this constant here is positive. Okay, because it's on the same direction. That's the first situation. And then the second piece of information we have is that the length of projection is the length of u times the cosine of the angle. And that comes from right triangles, right? If you use trigonometry here, the length of u is the hypotenuse, and this is the adjacent side. So cosine of theta is adjacent divided by hypotenuse. So that means adjacent is hypotenuse times cosine of theta. So with these two pieces of information, we can find the formula. From the first one, we have projection, the length of projection of u onto v. So if you look at the first one, that's norm of CV. Now there is a little exercise in the latest handout that I posted in Blackboard. You can actually pull a scalar out of the norm, but it becomes absolute value. Okay, that's an exercise. It's very easy to prove. So if you have a CV inside a norm, you can pull out the C, the scalar, and it becomes like that. Now because C here, we're assuming that it's positive, so absolute value of a positive, you can just repeat the value of C. Okay, now let's combine the two pieces here, this one with this one, okay, because both are the length of projection u onto v. So these two are the same. So that means C length v equals to length of u cosine of theta. And then from here we get C equals to length of u divided by length of v cosine of theta. Okay, so we have the conclusion here from this first case is that projection of u onto v is length of u divided by length of v times cosine theta. This is the constant. This is the multiple c, right? And then times v. So that's the c here. Okay, we found that in this first case. Let's look at the second case. The second case is very similar. We have two pieces of information here again. Number one, projection of u onto v is a multiple of v. So because it's on the same direction as v, but it's in the opposite direction, so we can see here that c is negative. Okay. The second piece of information is that the length of projection u onto v is again the hypotenuse. Okay, this is a hypotenuse times the cosine of this angle here. Now this angle here is not theta. This is 180 minus theta. Theta is this one here. Okay, 180 minus theta. Well, we can actually write cosine of 180 minus theta as, in terms of cosine of theta, is just negative of it, negative of cosine theta. Okay, so cosine theta is a negative number, but we want the positive here, so we put minus cosine theta. Okay, you can check this. It's a simple trigonometric identity. Cosine of 180 minus theta, 180 degrees minus theta, is negative cosine theta. Okay, and then again, length of projection u onto v. According to the first one here, the length of that is the length of CV, which is absolute value of c times the length of v. Let me move this over here. Okay, I can get rid of the absolute value, noticing that c is negative, so absolute value of c is negative c. Okay, think about it in terms of a number. Let's say if c is negative 2, then absolute value of negative 2 should be 2, right? So I can write absolute value of negative 2 as negative 2. So that's what this means. So absolute value of a negative number is minus that negative number. Okay, now let's combine these two pieces, this one with this one, so those are equal. So there we have equals to absolute value of u minus cosine theta. If you solve for c, then again it will give you the same formula as this one, because the negative signs will cancel. So again, we have the same thing. Projection u onto v is cv, which is norm of u divided by norm of v cosine theta times v. Okay, so in both cases the formula is the same, so we can simply just write one formula. No matter what case you are, or first or second case, projection of u onto v is norm of u divided by norm of v cosine theta times v. Okay, we found a formula for projection, but in fact that formula is not so nice. There is a simpler formula, because if you see here that if you compute that, this is square root of inner product of u with itself divided by square root of inner product of v with itself, and then you have to find the angle, which is another. There's a formula for that angle, so it's a very complicated way of finding projection. So we can simplify things here if we put the formula for cosine of theta. Okay, here is norm of u divided by norm of v. If you all remember the formula for cosine of two angles, that's the inner product of u, v, cosine of an angle between two vectors. It's inner product of u with v divided by length of u times the length of v. And this is times v. Okay, so this whole bunch of things here, this is just a real number. Okay, v is a vector, so it's a scalar times a vector. Now let's simplify this scalar here. See, this will cancel with that, and then norm of v times norm of v is norm of v squared. Right, norm of v squared. That's square root of v inner product with v squared. So we can cancel. Right, we can cancel the square root in there. So this becomes projection u of v is inner product of u with v divided by inner product of v with v in the direction of v. So this is a much nicer formula. Okay. You don't have to find the angle between the two vectors to find the projection. Let's see an example. Okay, so let's say in R2 with the dot product, right? If we have u, v being u dot v, that's the dot product. So for example, let's say u is, so let me draw a little picture here. So let's say this is 1, 1, and this is okay, let me write, okay, well, let me give a better example. Here's 2, 1, and then here is, okay, 1, 1, 2, sorry, this is 1, 2, and this is 2, 1, there we go. Okay, this is my vector u, this is my vector v. I want to find a projection of u onto v, so if you do the projection, it will be this little vector here in red. So that's the projection of u onto v, okay? It's not the whole vector, the black is not v, it's just this little shadow, okay? Form an angle 90 degrees there. So what is this vector here in projection? Okay, u is 1, 2, v is 2, 1. Projection of u onto v is inner product of uv, according to the formula there, divided by inner product of v with v in the direction of v. Okay, the inner product that we're going to use, because this is R2, we usually use the dot product. So this is u dot v divided by v dot v in the direction of v. Okay, u dot v, that's 1, 2 dot with 2, 1 divided by 2, 1 dotted with 2, 1. And v is 2, 1. Okay, now this is a number, okay? This will give us a number. It's a scalar. Let's see what that is. Numerator, 1 times 2 is 2, plus 2 times 1 is 2, that's 4. And then 4 plus 1, that's 5. So this is 8/5, 4/5. So that's the projection. Okay, so this is a simple example in R2. Let's look at another vector space. Let's say C from 0 to 1. Okay. We're going to use the inner product uv to be integral from 0 to 1 ux vx dx. Let's say now u is x and v is x squared. Okay, again, now this, if you do the diagram, this would be an abstract vector. Here u, which is simply x. Okay, this vector here. And then here is a vector v. So the projection of u onto v will be what? Notice that without calculating the projection, I know that projection is on the same direction as v. So that means whatever I get in here, whatever this vector is, it will be a multiple of v. Okay, so it will be something, a scalar times x squared. So in other words, whatever I get here will be a quadratic polynomial. It will be just something, a scalar or a number times x squared, because it has to be on the same direction of x squared. Okay, let's find projection now. So let me copy this, put that in here, so I can save some time. Oops, it didn't work. That's okay. uv. So that's the formula for projection. Now on the top here, inner product, that's integral from 0 to 1 of x, that's what u is, times x squared dx. And the denominator is integral from 0 to 1 of x times x, oh wait, it's v with itself, so it's x squared times x squared. And this is times v. Okay, so you can see that this would be a number. This is a scalar here. This is a number. Okay, projection of u onto v. The numerator, this would be x cubed, and then x to the fourth over 4, so this would be 1/4. This is x fourth, will be x to the fifth over 5. So here you go. So that is 5/4 x squared. So the projection of x onto x squared is 5/4 of x squared. Okay. All right. Notice that projections depend on the inner product. Now let me show you an interesting situation. We all know that what happens if the two vectors make an angle of 90 degrees. Let's say here is v and here is u. So this angle here is 90 degrees. So that means that the cosine of the angle should be cosine of 90 degrees, which is 0. So we can expand that to vector spaces, saying that we say that u and v are orthogonal. Okay. If cosine of theta, if the cosine of the angle between them is 0. Well, cosine of the angle being 0 means that, okay, let's see, what is the formula for cosine? This would be inner product of u with v divided by length of u times length of v equals to 0. So I can multiply these two sides by length of u, length of v. So this really implies that the numerator there should be 0. Okay? So in fact, that's the actual definition. So I can go back and forth here. So let me replace this definition here. Let me say that u and v are orthogonal if the inner product between them is 0. That's another definition here. We define orthogonality between two vectors through the inner product. Okay. So we have two definitions of projection and orthogonality of two vectors. I can show you two vectors that are orthogonal. For example, in R2, if I do u as being 1, 1, and v being 1, -1, so if I do the inner product between them, which is a dot product, okay, in this case. So this is u, v. Okay, this would be 1, 1 dot 1, -1. This is 1 minus 1, that's 0. So u and v are orthogonal. Okay. Here is another example in C0 to pi, continuous functions on the interval 0 to pi. Here I'm going to pick u being sine x, and then v here is cosine x. Two functions in this space of continuous function. All right, let's find, and the inner product that I'm going to use, using inner product integral from 0 to pi of ux, vx, dx. Finding the product of these two. Okay, u times v, that's sine times cosine. Well, it's the vector sine product with vector cosine, okay? It's not a product of functions, it's a product of vectors, it's an inner product of vectors. Okay, this is integral from 0 to pi, sine x cosine x dx. And this integral, okay, so this is this is already the derivative of that. So this would be sine square x from 0 to pi. So this is sine square pi minus sine square 0, which is 0. Okay. So that means u and v, or we can say sine x and cosine x, are orthogonal. They make an angle of 90 degrees. Now again, don't confuse orthogonality of graphs of those functions, because it's not the same thing. If you graph this function, it would be something like this. Cosine is something like that. It has nothing to do with the graphs of those functions. It's in this case, in this space of continuous functions, they are considered vectors, and using this inner product, they're points in the spaces in the space of continuous function, and it turns out that the diagram for them. So here's sine. Okay, so I don't know. The sine is someplace in there. It turns out that cosine is perpendicular or orthogonal to cosine in this space of functions, continuous functions from 0 to pi. So sine and cosine make an angle of 90 degrees in this weird space of inner product space. I forgot. Now I notice here that this should actually be over 2, right? This is u du, so it's u squared over 2. I forgot to put that, but it would be 0 anyway.